This presentation is made to describe you what is the DRIHM paradigm. Let's say how DRIHM has been developed from the needs of HMR, hydrometeorological research scientists, to the requirements we ask to ICT people in order to solve some of the problems we have and to make even better way of predicting intense and extreme events, as Professor Sicardi described before. So the idea of this talk is just give you some motivation of the DRIHM project and show you the Mediterranean area and generally show you a paradigmatic event and see how the DRIHM infrastructure has been designed in order to help us in making better prediction and making better evaluation of such intense events. So basically the motivation are based on EM-DAT statistics, but also on the knowledge that all of us has that flood events and meteorological events are basically most ravaging events and caused by a lot of damages in order damages of, let's say, economic damages, but also a lot of loss of people lives. So the right panel you see there show the number of people affected by such natural disasters. So the starting point is try to make better prediction and evaluation of such events, such as droughts, but floods in particular for rain and storms are the two most likely events in the last years. So this is an image that shows you how these events are actually affecting almost all the world. There is no part of the world that is not affected by such disastrous event. Let's say, so all the events are, let's say, at the world level. So working only on, let's say, maybe on a state basis or on a few state basis is not actually the way. So what we want is having some tool that can be used at the pan-European and maybe at the world level. We start from, let's say, we focus for developing the project on the Mediterranean region, starting from the early 90s years, and where the FLASH project estimated a lot of the 29 billion of euros of damages, only material damages produced by flood, without considering the people affected. The casualties have been estimated over 4,500 in the Mediterranean area in this period. So let's say having tools and improving tools that maybe will be used also for operational purposes is actually an important and a very crucial thing. So the idea was that so we started as before starting DRIHM in try to understand which is the way of classifying severe storm. In the next slide, I will show you some results of research done at CIMA Research Foundation that is leading the project on the severe storm, and see how we can classify them, how can let's say try to have give to people that have to predict them better tools to do it. So we started in order to simplify and to have a measure of this event and classify two types of event. The type 1 events are the long-lived, so lasting more than 12 hours, and spatially distributed events. While the type 2 events are briefly, brief and localized, less than 12 hours, and in space less than 50 by 50 kilometers as area. And we try to understand if there are some differences between these events, if there is some way of predicting one type of event and maybe see that the other type is more difficult to predict, see what are the tools we need to improve this research. So we see that in doing our research, we have some equilibrium condition and non-equilibrium condition. The non-equilibrium conditions are associated to very low degree of predictability. So basically, just to give you a quick look, the cape is, as you see, built from large scale, but is not removed continuously. It's just suddenly removed by a very intense event, and this is something that interests us a lot, because these events are very difficult to predict. As you see, here there is a very low degree of predictability. So the type 2 events are very, very difficult to predict. While there are some other events that maybe affect the same area, but have a completely different structure, and they have an equilibrium condition that drive to high degree of predictability, because the cape that is created at large scale is continuously, let's say, consumed but by convection at smaller scale. So basically, you don't have very ravaging events like the one that Professor Siccardi showed you, but just a continuous storm, and let's say you may have severe, intense rainfall event, but these events are, let's say, a spatial distribution that is completely different, and let's say the intensity is not so unpredictable as Professor Siccardi showed you before. Then, let's say, I don't want to go too much in detail. You see, so we found out that there is a time scale. This formula, so the way that cape is, we can do the ratio between the cape and the precipitation rate and have a value that is basically distinguish the events that are very intense but predictable to events that are maybe are intense but have inside an unpredictability level that give us really ask us to better improve the models and better build up chains such as the one we will face during this school. So basically we find out that, let's say, when this number is let's say greater than 6 hours, you have non-equilibrium conditions. So basically you have the cape is accumulated, and then suddenly in few hours you have the consumption of cape, and then you have a very, let's say, extreme event. While in the other condition you may have intense event, but let's say the cape and the precipitation rate are always in equilibrium. So basically the event you have are very intense but not so unpredictable. We made some research, let's say, on that. We classified all over Italy 81 severe events from 2006 to 2009. We have 51 events of type 1, so lasting more than 12 hours and on bigger area, and 30 events of type 2. So these are the most ravaging events. And you see here that all the type 1 events have, this is one case, but let's say for all these events that we show you later, this convective time scale is basically less than 6 hours. Means that basically the intensity, so the cape and the precipitation are always in equilibrium. While when with type 2 of event, and this is another example, you have no such equilibrium. You have a lot, let's say, the accumulation of the cape, and then in few hours you have a lot of precipitation to be again in the equilibrium phase. And these are all the events we have considered. So in this part you have non-equilibrium, in this part you have the equilibrium. So basically the shortest events are always the events that are in a non-equilibrium phase. So the most difficult to predict, and also the most intense in terms of precipitation in few hours. And then let's make a step more. At the beginning of this project, there was, and described by already by Professor Siccardi, an intense event in Genoa in November, at the beginning of November 2011, where in a very small area close to the center, let's say the area that Professor Siccardi shows you, you have basically 500 millimeters of rain. So as you see here, a third of the average annual rainfall for this area just fell in 5 hours. This is the general condition are non-equilibrium condition. So basically, let's say you have, let's say, such big amount of rainfall that, let's say, between 10 and 3 o'clock p.m. UTC, you have 500 millimeters. Let's say only 6 people were killed. I say only because, let's say, the event was so intense that was, let's say, much more than 6 people can die during this event. Only 6 were killed. You see here an image where you see floating cars and people wading in depth through the flooded streets and so on. And this flood is very similar to the one that hit the same area in 1970. So, because the urban tissue is the same. So basically, when rains a lot, you see here, this is the river, the Bisagno River before the inlet that Professor Siccardi showed you. It's just, let's say, started flooding the closer area. And this is, let's say, the situation is actually the same like in 1970. So what we can do is try to build up better tool to understand and maybe try to predict such events. This is a graph of observed rainfall from the rainfall depth from 9 UTC to 3 p.m. UTC. And you see the maximum value is 500 millimeters. And in 24 hours, you have such a situation. But you see that in this area, basically, all the precipitation is concentrated in these 6 hours. So this is, from the paper I showed you before, a more general view of what, let's say, what was the situation in the city. So you see the satellites showing the situation and the general circulation. So, okay, the event is very local, but you should always have a look at what happened, let's say, not only in your garden, but let's say outside, and which is the general situation of the weather. And this was not another picture that show you the mesoscale situation. So larger scale, so synoptic or even larger scale, mesoscale situation. This is the circulation. Here the flow was coming up, and here the flow, so no, here is the coming down, and here is coming up. So you see, and the precipitation developed along this narrow line. This is the radar images. You see the structure were stuck in this position and stayed there for hours, more than 6 hours, exactly in the same position with the same intensity. And that's really, so what is important is also understand the process at different scales, starting from the synoptic scale to the mesoscale, and then even microscale. So you see, even if it's not so easy, but you may have some, say, glance on what is the microscale structure of the atmosphere, and see here you see just in front of Genoa some tornado and water sprouts very close to the area where we had the event. Here, so from the atmospheric point of view, but also the sea has a role that is very important, because is not just the atmosphere and then the sea is, so they are 2 worlds apart. They are in the same world. And as you see here, there are the same picture made with 2 different sea surface temperature anomaly made from 2 different, one from US satellite and the other from European satellite. But as you may see, this is the rainfall structure that hit the city of Genoa. And you see here and there, you have the same anomaly of temperature of the sea. And this is another important ingredient in building up such an intense event. So always have a complete look at the events you are considering. Not only give a look at, let's say, the hydraulics, not only the atmospheric model, but try to, maybe you are an expert on the weather forecasting, but try to have always a look to satellites, sea situation, hydrological model, hydraulics model, because this complete view help you and us in understand better what is going on. So this is the cape that in the last hour was actually above the threshold we have calculated. And this is another example. Just 10 days before the Genoa event, we have a very intense event with even more death in the eastern part of Liguria region with a really similar structure. You see here, and I can speak for days about these events. So, why DRIHM? So, as you see here, this event challenged our current scientific understanding and call for, let's say, not only hydrometeorological research, but some effort that goes over the simple hydrometeorological research should also take advantage of the ICT research, because we need ICT in order to run more model in terms of maybe ensemble. If I am a meteorologist, okay, instead of having a simple model, I want to have an ensemble model in order to evaluate the situation. But also because I want to evaluate the hydrological impacts, the hydraulic impacts. So to understand, explain the physics of the process, understand if these phenomena are intensifying or not as a climate variability in the Mediterranean region and maybe in other parts of the world. And then see how I can take advantage of increasing both the computational power through ICT, both using the grid computing that allows me to run maybe more instances of my models, or using the petascale computing system. Let's say in order to run my model and maybe my meteorological model at higher spatial and temporal resolution. So that's the conceptual showcase of DRIHM. Basically, we define, I will show even later, 3 experiments. One experiment is devoted to the meteorological models. The other one is devoted to the hydrological models connected to the meteorological prediction. And the last experiment suite is devoted to hydraulics and effects of such precipitation. So try to have a complete chain from the prediction to the impacts of such an intense event. This will help us in understand better all the phases of prediction, but all the phases of such processes. And we did it not only in the DRIHM project, but we started with the DRIHMs. That was basically a study about what we can do with the idea of DRIHM. So which were the requirements of different people working on a different level. Then start with the big project, the DRIHM, and the school and the research we were doing on it. And then there was, and there is, the DRIHM to US, that it was, let's say, a study of DRIHM about interoperability of systems. So, okay, Europe can develop its own system. What has been developed in the US? How can the two systems talk together? Is there a level of interoperability between systems? Can we take advantage one of the research of the other in a seamless way? And then we started with DRIHM to US project. So this was DRIHM, and we have the white paper of DRIHM. I think you have in your bag. And this write just the requirements that we try to develop during the DRIHM project. So the ICT challenge of DRIHM is try to collect each research center as, for instance, develop his own chain, his own prediction chain. I put some meteorological models, some ensemble models, some downscaling models, some hydrological models, some hydraulics model. But each center, each research center is separated by the other. There is no connection between them. So I have my own chain, the other people has his own chain, and they do not speak each other. So basically, as you can read here, I have the model I and the model J. So the model I at the meteorological level speaks with the model J at the hydrological level, who speaks with the model K at the impacts level. But if I have another model, how can insert it in this chain? It's not easy, so we need the help from the ICT people. We need that from the ICT research in order to do that, in order to make so possible to use also models that other people develop, and then they give it to me in a standard way, and then I put on my chain, and without a month of work I can run them and have results comparable with mine, and see which are better, which results I can have, and what explanation I can find from this event. So why DRIHM? We know that having a better forecast is our aim, but of course storms do not respect any boundaries, so we need a pan-European approach. As you can see there, this one, the event of the 4 November event I showed you before, started just in the US at the end of October, and So you see there is a connection between what happened in a part of the world and what happened in the other. So bear in mind these things. Everything is connected, and we should have a very complete view of that. So I will show you some slides. Of course, people, ICT people will show you and explain much better than me, for sure. But let's say what you have in mind, and you are DRIHM users, and you interact with the DRIHM portal. Then all the ICT people develop all the things that are, let's say, beneath the portal that you usually do not know. We see, you run your model, and you do not know if you have grid resources, non-grid resources, praise, Windows, single computer, clusters. You just, with DRIHM, just, okay, I want to run my model. Okay, I put my model there, I run it, and I do not, as HMR scientist, I don't want to know too much about how it will work, let's say, which are the ICT details. But let's say that's why we build up the DRIHM infrastructure, because it's a very complex system, but for us as HMR scientists is not very, let's say, we don't see it. We just see a portal, and it's very simple. But beneath the portal, there is a very complex way. It's like in a shop. You can go and build and buy something, but beneath let's say, there are people that works and try to make all the things work well for you. So the idea, again, is the DRIHM user interact with the portal, where some scientists define and develop the model and put the model inside this big system that will be described better than me by the other ICT people, with praise, EGI, so read, supercomputing, and other resources that can be available at the European level. And then, but you just go there and say, okay, I have to run this model. You, through the portal, try to make this configuration, make a job submission to this system, and have back the results. And so basically, you start with, for instance, with rainfall, the first level, we have many meteorological model, WRF, in two versions, meso-NH, there is in the Rome, there are French rainfall, there is a downscaling model I will show you later today. So basically, way of generating rainfall from prediction and from observation. You have the discharge layer, where you have many hydrological models that you can use. And this is not really common way of things, because to put together this different model, maybe, let's say, now is useful, but let's say, usually people that use this HBV do not use drift or ribs, so and have different results. In this way, we can compare output of this meteorological model passing through this hydrological model and see what happened at the water level flows and impacts as a third experiment. So this is the portal architecture. I don't want to bother you too much, because other people will explain much better than me. So I can just show you how complex is. One thing that you will see is very simple. from outside. But inside is something that is very needs to be developed in a really good way. And this is the portal. You see, okay, use a critical case, yes, no. Yes, you want to include a meteorological model, and you choose which one. I want to use an ensemble to create a stochastic ensemble of this output. I want to choose an hydrological model, and then you can choose from really simple, in a really simple way, these models, and then you can upload or not, and then we will show you in next presentation how to do it. You can upload the data you have or not, and then you can say configure and run them. So basically, while at the beginning I can do just WRF, rainfall, drift, and stop. So I cannot use the other model. Now we have developed a NetCDF-CF bridge. Basically, all the models talk with this, and this is able to talk with all the hydrological model we have. We use another standard for rain gauge observation and stream flow observation, that is WaterML. And basically, you see, I can choose which, doesn't matter which is or maybe more than one meteorological model, more than one hydrological model, and see which is the results and which are the prediction for such intense event. So going back to the meteorological scenarios of the event I showed you before in Liguria, you see that you may have more than 30 high-resolution multimodal scenarios, 3 different ensembles, but every model and every output is very compliant with the same standard, the same format. So you need, basically, you can just process them with only one system. So if your data are meteorological data, all the meteorological data came out in the NetCDF-CF format. So this allows you, no matter which model produce your data, basically you can compare them. And this is, let's say, the Bisagno catchment. We run different models. Arom, the red, WRF is the green, while the blue and this one is the meso-NH model. And this is the average prediction of rainfall over the Bisagno catchment. And the black one is the observed rainfall. You see that you have many models, and one of them, the blue one, is doing better than the other. So you can try to understand which one is going better in post once the event has been you have this, let's say, development has finished. But or also during the event you may have an ensemble of multimodal, or you can use like in this case ensembles of the same model. And you see here the prediction, so the ensemble prediction of accumulated precipitation over the Bisagno River from 2 different models, the Arom and the meso-NH. You see the meso-NH is much better in terms of resolution, is doing a really good job in predicting the total rainfall of over the Bisagno catchment, while the Arom, there is not, is a different model that is hydrostatic, while the meso-NH is not hydrostatic, is doing let's say, a worse prediction. But you can compare them. You can try to build up and compare different models, and before was not possible to do that. So there you see, three different models, Arom, WRF, and meso-NH, in terms of precipitation, in terms of wind. And you see that you can easily compare them in the same, let's say, in the same way, using the same kind of graph. So everything is very easier for you because you can just have a comparison of them. And here is the hydrological effects. Here you see the precipitation, and here you see the discharge of the hydrological model RIBS with the meso-NH input. So the meteorological model is meso-NH. You see the blue line is the rain observation, of course, in the future. The red line is the meso-NH prediction, and the black line is the observation in the past. So I can go, and you see the rainfall prediction and the discharge predicted by, simulated by the model. But then you can combine. Instead of using, here you use RIBS as a hydrological model, then here you can use drift. There is another model. And this is, let's say, a seamless change of the model, because you can choose basically which hydrological model you want to run with the same input and see which are the differences in the output. And this is drift both with the Arom model and the meso-NH. And you see drift with the meso-NH, you have basically a correct prediction of the event. So this part was before DRIHM. Okay, before DRIHM I can use only WRF, maybe with rainfall, drift, and stop. Then maybe Professor Garrote can use rain gauges observation with RIBS and stop. Now with DRIHM, I can just say, okay, I have all these models that can speak, all these meteorological models can easily speak with all these hydrological models. We can easily produce a standard output that can be used for let's say, hydrological evaluation or impacts evaluation. That's the difference. Before, I was just stuck to few models. Now, I can use a lot of models that are compliant with these standards. So, this is just a description of DRIHM to US. So, thinking globally, as I say, we cannot just, okay, the events is maybe it's just in a very small area here, but let's say we have to look to stay at the world level in order to understand which kind of process we are facing. And that's why this, and during this school, you will have the opportunity of having a look at how these two projects, DRIHM and SHIM, talk together in the DRIHM to US. So DRIHM to US and SHIM talk together in order to compare and share experiences in this common, let's say, way. This is just a test bed of the different interoperability of the model between the two projects. And at the end, say if climate change Okay, but now I've built up a better, let's say, tool in order also to take, let's say, climate change in my models, because again I can start with the meteorological model, including also models that take care of the climate change, and then, but it's always a seamless approach, because I have climate change and a meteorological model, hydrological models, and let's say hydraulics model that talk together very easily. So, thank you. This was a really quick overview. During the school, you will have the opportunity of develop all these things, but that's all for now. Thanks. So if you have questions, okay.
Thanks for the presentation.
Yeah.
I saw that you use several meteorological models, like one model or different version.
Yeah.
First point is, do you have any kind of pre-processing before it goes to hydrological modeling, because different meteorological model is different?
Yeah, let's say this kind of, I will show you here. This NAT CDF-CF in terms of precipitation allows you to have, let's say, the precipitation output and the other output needed, let's say, produced by the meteorological model to be, let's say, written in a standard way that can be easily used by the hydrological model.
I did ask this one. There's like the formatting to reading the models. But before reading the models, you need to have a pre-processing, like bias correction for it.
Yeah. Each model has its own, let's say, way of going in the NAT CDF. So for each model has been developed a tool to make it compliant with, if it is not, with the NAT CDF-CF. So at the end, you can use them, let's say, free.
And the second question is, like, as you're based in Europe, I tested work model as well as ECMWF forecast, both for the hydrological perspective. And the result of ECMWF is better, especially if you want to go for a longer lead forecasting.
Yeah.
Because the work model after 3 days exactly nothing as an accuracy perspective.
Yeah.
So why not you use any ECMWF?
Let's say the very rough answer is that before ECMWF was not in the project. Let's say in the next part of the project, ECMWF will be part of this project. So they will start. They are interested in the DRIHM idea and see how they can, especially from a climate perspective, how can fix it and how can use the model inside this idea of developing stuff. Sure.
Hi, Nicola. I have 2 questions.
Yeah.
The first one is about the model chaining.
Can you speak?
The model chaining?
Yeah.
Is it a fully coupled approach, or is it uncoupled in terms of how the models teach each other?
Yeah. Okay. At this time, let's say as you see from the arrow, you have, let's say, from the meteorological model, you pass to the hydrological model, then to the impacts model.
So is it a case where the meteorological model has to complete its simulation before the outputs are passed?
Yeah. And at this time, yes, let's say, can be developed, but at this time we are.
Okay. Right, and the second question, you spoke about ensemble runs using different models, but is it possible to have ensemble runs using one particular model where you change the parameterization or something?
Yeah, let's say in this way you may have, if I understood properly, many run of different models, or the different model, or some of these models can be run in an ensemble way. So let's say you may choose and compare if it's better, let's say, to have let's say Pullman ensemble model, say using different models, the output of different models, and see maybe the ground effects, or maybe use only one ensemble and see which is the output of these models. Thanks.
In this structure, where is the climate change scenarios? I haven't seen any climate change scenarios. Are you using or not?
No, let's say the climate change part will be the future of DRIHM. Let's say, because of course, let's say we can add in the meteorological model takes into account also a climate change model.
Because you can't model for the future by using observation, because you can't model people's behavior for future. So you need climate change scenarios by using
IPC. Yeah,
so you need some general circulation model outputs for regional climate model.
Yeah, that's it. We can do it. Let's say at this time, because we have to develop not only the hydrometeorological idea, but also all the ICT part of combine them in order to be in a kind of, as I said before, equilibrium. Because if not, if we develop only the meteorological part, we were in a non-equilibrium phase with all the meteorological things, hydrological things ready, and the ICT part that would be not ready. So we have to, let's say, develop these things, and then in hopefully in the future, in the next proposal of we are preparing, we will all the things will be devoted more on the climate change aspects of the problem.
You may have made in collaboration with ICT from a kind of famous climate model.
Okay.
Can you please go back to the previous slide, 42? To 42. I'm sorry.
42.
Yes.
Sorry.
So let me see if I understand you correctly. Here you use the prediction, which is not really close to the observed values, with another model, hydrological model.
Yeah.
And at the end, the hydrological model gave pretty decent results.
No, let's say I use two. Let's say I use the same hydrological model, but with two different inputs.
Yes.
One from Arom, and there is a hydrostatic model, and one from Meso-NH, there is a non-hydrostatic model.
Yeah.
And you see, using the same hydrological model, but two different, let's say, prediction made by a numerical model, you may have, of course, really different. Of course, Meso-NH is doing better prediction because it's a non-hydrostatic, so takes care of some of the features that are very important for the event we are considering. Maybe if we consider a stratiform event, maybe using drift and Arom and drift and Meso-NH, basically we have no differences. But for such event, it's really important to go to really very small scale. Okay. So if you have no more question, we can. You have last question. Okay.
Why you limit the grid data?
Can you because
The grid data is limited for 0 point. Well, it is limited for this area.
So the limit of
The grid data. The grid certificates,
No, I actually do not understand your question.
the grid data
Yeah.
is limited for your country. Why it is limited for one year?
Let's say it depends on actually the model you are using. Let's say it depends. Maybe for instance, aroma has a bigger domain, mesonage has this very small domain. It depends on the resolution you have. Last.
Connected with this question, because you said that the grid resolution of each model has different grid resolution,
Yeah.
and yet you compare those models.
Yeah.
Is it? Do you think?
No, let's say this is to show you the potential. Of course, if you use, let's say, higher resolution model, it should be in principle better, but it's not always true. Because maybe, let's say, a meteorological model, even if it's as a, let's say, a little bit coarser area of prediction, is better in terms of the total amount of rainfall. While if you consider a meteorological model at smaller scale and you consider it at actually the very high resolution, maybe he predicted the total, the total amount of rainfall, but it put it on the wrong place. So from the hydrological perspective, this is a nightmare, because say, okay, will you be concentrated on maybe some catchment and the event is produced on the other one. So that's it. You have to always consider these two things.